Hi everyone, Zach here, and welcome to the prep video for lesson 31 of this series on developing a survival game. In this prep video, we will discuss materials. This video and this series have been brought to you by my Patreon sponsors. Okay, so what are we covering in today's tutorial? Well, in today's tutorial, we'll create our base water material and a material instance for that. Before we get into that, let's discuss some key terms that you'll need for this prep video. So, in terms of key terms, I've split them into two groups. First, we have shader. And a shader is what we see in the world. It's the final color of what we're looking at. It's what the object looks like. In Unreal, we refer to a shader as a material. A texture is an image used to make materials. In the other terms, we have our source color, destination color, and final color. Our source color is the material. Our destination color is already what's on screen. And our final color is what is actually rendered when this new source color is added in. A way to think about this is if we are looking through a window into a house. The window is the destination color. The items in the house have their own source color. The couch has a particular color, the chairs have a particular color, the carpet have a particular source color, but we're looking at it through a window. So the final color, the combination of window plus the thing we are looking at, will be different than the source colors for each. And we have two other terms that we should explore. Well, really one. We've already explored one of the two, that was material. The other one is material instance. So, again, a material is a shader. It is compiled prior to gameplay, and every time you make an edit to a material, you move a node slightly, you are required to recompile those shaders. That's why it takes ages sometimes to work with materials. You're changing something, or you open it and move something around, you have to recompile. On the other hand, we have material instances. And a material instance is a dynamic instance of that material. And we can edit the parameters that we've created in the material. So when we make a material and you make a parameter, those are things you can edit in the material instance without needing to recompile. It also allows for us to change the material at runtime. And we use material and material instances together for master and implemented materials. So if you look at the mega scans, for example, a lot of times the materials you're seeing on the screen are actually material instances, and there's a master. And if you apply that master, you're not going to see anything because you need to set the textures, and the textures are parameters in those materials. It might be we have a material like a chair, and we have slight variations to it where a chair is more weather worn in one condition, or has a different color, but we don't need a new material, we just need to change one parameter. So material instances allow for us to do that. All right, now that we've covered these terms, let's take a look at some key elements around materials. If you're already familiar with most of the stuff I said so far, the rest of this will be review for you. If you're new to Unreal or new to material shaders, these are some of the key things you'll need to know. So let's start with instructions. Every material has a set of instructions. This is the example from the prep file for our water material. So you can see it's a fairly complex material with 402 base instructions and 420 to 430 around our light mapping. All right, so what are instructions exactly? Well, it's a reflection of how complex the material shader is. It is what you are telling the computer to do every frame. So the way to think about this for an example, by the way, is you take your resolution. So the monitor resolution I am recording from, for example, is 2560 by 1440. So with this water material, with 402 instructions, every frame where I'm looking at the water and the water is being rendered, I am telling it to pass 402 multiplied by 2560 by 1440 every frame. That's a lot of instructions. That's 402 instructions per pixel. So the instruction element of it is you telling the computer, hey, you need to run this on these pixels. So you need to run this instruction, or a set of instructions, so 402 instructions per each pixel. And the more instructions something is, then the more complex that material is. Now, being more complex can reduce runtime, can make things go slower, but it's not always bad if something's complex. Small areas being rendered, thus pixels to worry about, take less time versus or less intensive than a large area where you're replicating the instructions for every pixel on screen. Then complex can be quite bad. And you can see this in the editor. If you go to optimization view mode, so where it says lit by default, if you click lit in the main editor, and you'll see optimization view modes, you'll see shader complexity. And if you look at our water when we're done, you'll see our water is quite complex. In fact, probably a bit too complex, and we should probably consider optimizing it down the road. All right, now that we've talked about the instructions, let's talk about material and material domain. So there are multiple domains. I have 3 on screen. I'll have 3 or 4 on the next screen as well. So let's start with surface. Surface is what we typically think of when we think of material shaders. It's what we typically see in the game world as a primary representation of that object. So walls, skin, floor, ceiling, the material of a bark on a tree, that sort of stuff. That is what we typically think of when we think of materials. So not much to go into there. We'll be focusing on surface materials for this video anyway. We then have deferred decal, which are used for, well, decals. So things like our dynamic character footprints, which we'll cover in section 4C, graffiti on walls, blood splatter, and this can both be dynamic or non-dynamic. So in the case of the footprints, that's a dynamic decal we're putting down. Then we have light functions, and we briefly talked about light functions back in section 3 when we worked on our flashlight, when we talked about IES profiles. So it's used for creating materials, well, with a light function, and it only works if cast shadows is enabled. Like I said, this is very similar to our IES textures. However, it is more expensive than our IES textures. Where you can use an IES instead of a light function, you should be using an IES. However, sometimes light functions are useful. And if you have a particular pattern or shape or something that might be dynamic, used for moving across an area, so moving shadows or moving lights or flickering, you might want to use a light function if you can't find an IES that matches the particular look you need. And then we have 4 others, which are volume, post-processing, user interface, and virtual texture. So volume is used to make materials for a 3D volume, so clouds. And we'll see this in videos 60 and 61 of this series, mist, fog, smoke, things like that. Post-processing are materials that are used, well, for post-processing. So you can create materials that will cell shade things, create images that are black and white instead of having the full albedo that we're normally seeing in a material shaders. Or if you think of Alien vs. Predator, the original 2 from like the late 90s, and the infrared, that would now be done using a post-processing effect of some sort, and you might have a material to help you set that up. User interfaces does what it says on the tin. Materials for user interfaces. And then finally, we have virtual textures, which are used for runtime virtual textures. So it runs on the GPU at runtime and not pre-compiled. An example from Epic for this would be splines that conform to the terrain is where you might want to use this. And then we have our blend. And there are different types of blend. And again, we have 3 here. We'll have some more on the other screen. So opaque is what we traditionally work with. So we have opaque, which is what we traditionally work with, and it's probably the easiest to understand because it's the most straightforward and the one that you will most likely use the most often. And the way opaque works is that whatever the source color is, so whatever our material is what we see on the screen. And it defines a surface through which light neither passes nor penetrates. This is usually okay in most cases. So plastics, metals, stone, some other things. Now, there might be some issues with this in terms of realism. You don't have subsurface scattering, and there are ways to turn that on, but we'll cover that maybe down the road. Next, we have masked. And masked, to be fair, really is quite simple to understand, but complex under the surface. So, really, this is a binary system. Either something is on or something is off. That's how you need to think about this. And we'll talk about that a little bit more in detail about how you know if something's on or off when we cover translucent, and we'll talk about the differences between translucent and masked. For masked, the way to understand it is that there are two outcomes. That the final color is either the source color or the pixel is discarded. And the way we do that is it checks if the opacity mask is greater than the opacity mask clip value, which is a value you can set per material. If it is greater, then the final color is the source color. If it is not greater than that clip value, then the pixel is discarded. So think about it this way. If I had a chain link fence, I could create a mesh that has every single chain, or I can create a whole bunch of bars that go across a area and other bars that go across the other area, so it appears that I've created every chain, but I've created an array of bars. Either way, I can do it those two different ways, where I have a lot of vertices, or I can create a plane with exactly 4 vertices, and then apply a material that looks like a chain link fence, where part of the material is being masked and thus not rendered, and other parts are being rendered, so that I now have a more performant way of creating a chain link fence. I don't need every vertice, I just need 4, and I make it look like there are parts that aren't there. And next we have translucent. And translucent is, again, easy to understand. Under the surface, it's a bit more complex. This is looking through a window, looking through a bottle, looking through some piece of clear plastic, what have you. Under the hood, the way this works is that the final color is the source color opacity, and source color opacity is the opacity pan in the material node plus the destination color multiplied by 1 minus opacity. Opacity color, or the opacity range, is 0 to 1. It is not compatible with dynamic lighting, unlike opaque and masked, and it does not support specularity. In fact, when we use the specularity node in the series for the next 3 videos, you might notice that eventually it grays out and we're not actually using it. Because it doesn't support specularity, reflections aren't possible with translucency. Now, you might have noticed in some games that, wait, some translucent surfaces like windows have reflections. How is this possible if they're using Unreal Engine 4? It's fake. They're using cube maps. In fact, there are games I can think of where those cube maps can be slightly problematic when the environment is destructible. I remember a game that had a translucent surface for some of their water, and it would reflect the area around it based on a cube map. But if you destroyed something in that area, say a light pole for a street light, and there's water nearby, the light pole still being reflected as being upright because it's part of the cube map. Now let's look at translucency and mask together, because they're kind of doing the same thing. First, you need to think about this in terms of black and white. Don't think about any other color. Just think about it as black and white for a moment. Where there is black, we either have no final color, so we're masked, or we're transparent, so this is a translucent one. Where it is white, we have opaqueness, we have albedo. This is where our color is coming in. So if you take a black and white texture and apply that to an opacity mask, and then apply a base color of bright pink, wherever the white is on the mask is that pink material. Wherever the black is, we're either seeing through it if it's translucent, or it's not being rendered if it's masked. So masked and black, not rendered, which is performant. We want that when we are looking at a chain link fence. But translucent and black, it is still rendered even though there is nothing there to see. And the reason for this is that it has light interaction still. So light passing through a chain link fence, it's going to pass through the holes in the fence. Light passing through a window, however, is going to bend and be manipulated by the cleanliness and by the density and all the other variables associated with that piece of glass. So while being masked is more performant, we sometimes do want translucent instead. And then we have additive and modulate, which pair well together. Additive is the final color is the source color plus the destination color. We're adding the source color to the destination. That's why it's additive. So it takes a pixel of the material and then adds it to the pixels in the background. If you've worked with Photoshop, this is linear dodge, the add setting. Now, there is, with additive, especially if you get into Niagara, be aware of this, there is no darkening. Black is transparent. White is color. And if you think about this as grayscale, the more gray you pile on top, the more white it becomes. So if you have layer 1 where, the gray is 0.2, And layer 3, where the gray is 0.3, so source color and destination color, your final color is going to be 0.5. And this is great to use with sparks and steam, thinking about Niagara, rain potentially, holograms. And also, again, this is not compatible with dynamic lighting. Modulate does very much the same as what's up there, except for instead of adding it together, it multiplies it together. This is like the multiply blend in Photoshop. And like additive, it is not compatible with dynamic lighting. And now we have shaders. We're only looking at 2, and there are a lot more. And the 2 we're going to look at are unlit and default lit. So unlit is a material that does not respond to light. It is defined by its emissive and opacity values only. We will use this with decals, for example. And we'll use it maybe for some other materials as well. Whereas default lit is, well, the default shading model. And it's the most common we'll use. It is used for most solid objects. Light hits the object and bounces off it like it would in real life or simulation of it. As for the other modes, well, I have no plans to use those shaders in this tutorial series, so I will not be covering them. And to be fair, you can do an entire tutorial just on the lighting or shading models only. And finally, let's talk about one node we're going to use today that I don't see used often, which is custom rotator. So you have multiple types of rotator nodes in materials. Typically, the main rotator works on rotating from the center. Now, I'm going to confuse you in just a moment because it says up there that a custom rotator is a material node that rotates a texture. It takes an input and it rotates that input based on the center and angle. Right. Didn't I just say a normal rotator does it based on a center and angle? Well, when I say a normal rotator does it based on center, I mean the center of the image. But before we get into that, let's talk about angle first. So the rotation range or angle is a value ranging from 0 to 1. This 0 to 1 value represents 0 to 360 degrees. So at 0.25, so 25% of a full circle, a quarter of our rotation is 90 degrees. 0.5 is a half, or 180 degrees. 0.75, or 3/4, is 270 degrees. So we can rotate anywhere in that range. Now then we have that center bit. That center bit is a bit, well, different. The rotation center is simply the pivot point. Think of this like an origin on a mesh. And most rotators use the values of 0.5, 0.5. So this is the center of the texture. Whereas if we use 0.0, 0.0, we're at the upper left corner. 1 by 1 would be the lower right corner. So if you've done my RTS series, this is the same as the edge scroll. All right, that takes us through what we need to cover in today's prep. This video and this series have been brought to you by Patreon sponsors like Hanas, Rian, Quad Menson, 1Volt10, and Galois. And if you want to help support this channel, consider becoming a Patreon sponsor. Or, just hitting that like button down below. It really does help this channel out. And as always, I look forward to seeing you in the actual tutorial video, and I hope that you have a wonderful day.